Good morning. My name is A.Michalak, and today I will present the results of our recent work on numerical methods for solving the Kron's model. Together with Dr. Krzysztof Pomorski, during our recent research, we encountered the need to predict approximate values of the wave function and what's more importantly, the energy levels of the system before it is actually and physically built. As a response to this issue, a MATLAB code was developed, which I will show you today. Sorry. During this presentation, I will try to explain the formulas coming from the Kron's model, the transmission line equations used for this model, three numerical methods of calculating the wave function, one method for computing the wave function corresponding to energy levels and the values of that energy levels. And at the end, I will present how the code looks and show some sample results of what it produced. Okay. So, if we create two long conducting lines and between them at regular intervals dx, we connect a capacitor with capacitance little c and the inductor with inductance little L1 in parallel, of course, and then ground the bottom line, and then we will connect inductors with inductance little l to each segment dx of the upper line. Then we will get Kron's model. For this model, we can write classical transmission line equations. One, I will do this only. One of that equations is where the change of the in voltage equals the current at that point times the change in impedance, and a second equation when where the change in current equals the voltage times the change in conductance. For every dx, impedance change by I omega L, with L, which is big, we are defining as L little divided by dx. And L big is given in Henrys per meter, of course, as we define. And conductance changes according to the second equation by this times dx. Combining these two equations give 2 and the 2 before. Combining that 4 equations give us a system of 2 ordinary differential equations, which is shown here. This system is important as 2 of the 3 numerical methods are based on it. In combining the two equations further, we can derive an equation that shows the system simulates the Schrödinger equations, as you can see. We just need to substitute certain terms to get its one-dimensional form. The first, if we substitute the 1 times L, 1 divided by L as h bar square divided by 2m, and omega square c substitutes with energy, and 1 divided by L1 we substitute as effective potential. We are just getting an Schrödinger equation, where the voltage on each node is representing a Schrödinger wave function. Sorry. In all 3 methods, we use Euler's method, representing the derivative in discrete form as the basis of our numerical solution. In the first method, we rewrite the equation from the previous slide, this equation in Euler's method, in discrete form. After rearranging the formula and solving for V at position s plus 2, we get an equation that we will use for the numerical solutions. One numerical solution. Yes. The second method applies Euler's method directly to the system of 2 ODs, which was shown here. After a few transformations, we get equations for the next values of voltage and current, and that's the second our numerical method. The third method assumes that both the voltage and current functions are sinusoidal. We assume that the voltage depends on cosine of function alpha, and the current depends on cosine and a function of a function beta. Other than that, it is the same as the previous method, but we set up exactly the same system. We set up the same system of equations and solve it, but we try to find not V and I at the first point. We are trying to find alpha and beta. And then from defining functions alpha and beta, we can use previous approximation, for defining V and E, V and I. That was the all three method for solving the wave function. Now we will go to the method of finding the energy levels and wave function of that energy levels in the system. So the Hamiltonian in our system look like this. In numerical methods, we can replace the second derivative with a square matrix. On the main diagonal, we place the value -2 with neighboring elements equals to 1, as it's shown. All others elements are just zeros. This comes from the Euler's method, which we already used at the previous slides. The matrix has the same number of columns and rows as there are nodes in our system, in our Kron's model system. The effective potential here at each point is the inverse of the L1 values. So it is also represented as a square matrix, which with the same size but in this matrix, on the main diagonal, we have the 1 divided by the values of L1 on each node. The general form of the Schrödinger equation is, of course, this, and as follows. If we define two functions, or I should tell two matrix, let's say one is VQ and the other is DQ, and the first will be eigenvector of our Hamiltonian, and the DQ will be eigenvalue of the Hamiltonian. The energies of the next quantum states will be equal to the values on the main diagonal of matrix DQ. And the wave functions of these states will be given by the rows of matrix VQ. That's everything from the theory needed to build the code. Now I will present the code itself. The code is divided into several main parts. The initialization part, where we define the functions and assign values. The definition of the axis based on the area values, a menu that allows us to choose which operation we want to perform, so that the program doesn't always calculate everything at once. And the parts where each option's operation is described. To better show the code, I shortened some parts in this general explanation. They will be shown in more detail soon. In the first part, the initialization, we create the necessary variables and functions and assign values to constants. This section should be edited when we want to calculate results for new values, for new systems, for every new system in Kron's model. The first option allows us to check the effective potential in the system. It's easy to verify if its values are what we expected. The second option shows the first numerical method explained earlier. I will show this method. Based on the values V1 and V2, it generates all the following values of the voltage. The results are displayed as function plots. The third option is the second method, based on V1 and A1. And the parameters of the system, it calculates voltage and current functions. The results are displayed at the end. The fourth option calculates based on the third method. It numerically computes the next values of alpha and beta. And then calculates current and voltage from them, and again the results are shown in the plot. The fifth option calculates the energy levels and their wave functions. We create the trotter and potential matrices according to the equations shown earlier. We created VQ and DQ and extract the results here. Here we are extracting those results. This program shows the energy spectrum and the wave functions of the first 4 states. If it will be needed, we can easily generate more. Finally, I will show some sample results of our code. After selecting the first option, the plots of L1 values and the effective potential appear. In this example, we can see two potential wells. It is clear that V effective is the inverse of the L1. Yes, I forgot to mention that there is also a 6th option. As you can see here, the 6th option where the program calculates everything if it is needed. Here we see sample results from the 2nd option, that is the first numerical method. We see 4 plots of V values representing the wave function in the Kron's model. Yes, as you can see, voltage across line, the EPS value of voltage, and the real value of voltage, and the imaginary value of the voltage. Here are the results from the 3rd option, which is the 2nd numerical method. From the you can see we have a real and value of voltage, EPS value of voltage, real value of current, and yes, there is some mistake in the presentation. We add wrong plots. Here should be a real and imaginary value of voltage, and real and imaginary value of current. I'm sorry for that mistake. But I think that that mistake is only in the topics of our plots. There are some sample results of the 4th option. Which is the 3rd numerical method. We get the most plots of all option. We can also see the calculated alpha and beta angle values, of course, both real and imaginary, and real and imaginary value of voltage and current. The 5th option presents the energy spectrum and their wave function, as I told earlier. For this sample values of our constants, and the functions present as it shown. That will be all. The presented code is the first step in our attempt to develop numerical solutions for the Kron's model. As the title of this presentation suggests, we plan to continue working on it. There are many things that can still be added. For example, vector potential, but that will require much more work on both the code and the theory. I hope the results we have so far are at least satisfying for you. Thank you for your attention, and goodbye.